Okay, so I guess to finish, something a little bit different. So I will talk a little bit about the context of my work in terms of impact craters, but this is mostly about magnetism, and we're moving as well from the Earth to the Moon now, specifically. So this is some work that I did mostly during my postdoc at MIT before I moved to Oxford, looking at the paleomagnetic signals in basalts collected during the Apollo 17 mission, and trying to understand what they tell us about the lunar magnetic field history. So it turns out that the magnetic field history of the Moon is quite weird. So we think that we have lots of evidence that the Moon had a dynamo. And so by a dynamo, what I mean is that you have vigorous convection from a metallic core, and that's driving a planetary magnetic field. And that's quite a surprising observation for the Moon. Partly because its core is actually very, very small. So the core is only about 1/7 of the radius, whereas for Earth, the core is about half the radius of the planet. So it's very, very small to start with, and obviously it's at the center of a much smaller body. So it was a bit of a shock that it existed at all. To start with, we didn't know that the Moon had a metallic core. And then it's also surprising that it had a metal component that was liquid, in fact, which is sustained to the present day. So just to show you what the magnetic field record of the Moon looks like, so here I'm going to show you a plot with paleointensity. So that's the ancient magnetic field strength, and it's on a log scale in microtesla. And then I'm showing you time on the x-axis, and that's going back from the present day on the right-hand side, so kind of the very beginning of the Moon's history on the left. So to give you a reference point, Earth's magnetic field today basically sits in this blue region, depending on where you measure it and how much it's fluctuating, but it's always within that blue bar. So that's what we see for Earth today. So a much bigger planet with a much bigger core, generating really quite an intense field. And we think that anything weaker than 0.1 microtesla, which is a very, very weak field, can't be attributed to actually having an intrinsic magnetic field. So anything weaker than this must be an external source of magnetization. It can't be a record that's actually being generated by the planet itself. So those are kind of our two reference points to bear in mind. And now all my colored points represent paleomagnetic measurements that have been made on returned Apollo samples. So there's lots of studies. In fact, this isn't even up to date anymore. This is all the studies that were done up till 2020 that have recovered the strength of the ancient magnetic field. And this is a really surprising record for several reasons. So firstly, we can see up here that we have lots of very, very strong intensities. So early in the Moon's history, it was actually generating a field at least as strong as Earth's, which is really, really surprising given its small core size. And then the second thing that's also really surprising is how sustained it is. So we have these two data points more recently, which definitely have not recorded a dynamo-driven field. So we know as of 0.9 billion years ago, the Moon has not had its own intrinsic magnetic field. But this one data point, which has a big error bar on it in terms of its time, even if we take it back to the oldest estimate, it means that the Moon was sustaining its magnetic field for about 2 billion years. So we have a very, very long record and a very, very intense record for the lunar dynamo. And that's a bit of a problem. Because if you just do some simple back of the envelope calculations, and if you were really, really generous with how much energy the lunar core has, so if you give it an unreasonably large amount of radioactive heat very early in its history, if you really ramp up the gravitational energy in the core, the latent heat and the thermal energy, if you kind of make these all as unreasonably big as possible, then the strongest magnetic field that could be sustained across the lunar history is only 2 microtesla. If we want to sustain a stronger field, then we can only sustain it for a small amount of time. So we can get up to about 20, 25 microtesla, but only for a very short time period. And that's actually not strong enough to explain these data points up here. So the observations and the models just can't be reconciled at the moment. And this is something that a lot of people in the community have been actively working on for at least the last decade. So this isn't really a new problem. So some outstanding questions that the lunar paleomag community think about is, are we actually not looking at a dynamo record at all? Is something else going on here that we've just not thought about? But if it is a dynamo generated by that core, can it just be generated by internal processes, so things like compositional and thermal convection of that core, or do you actually need to have something that's kind of vigorously mixing the core from the outside? So do you need some sort of external energy source that can cause that? And so this is kind of where my project came in. And what I was interested in thinking about was, rather than the strength of the magnetic field, which we've now got lots of samples and lots of data on, it's very, very difficult to get the direction of the magnetic field. And this would be a really, really useful additional constraint for these dynamo models. And so I looked at a sample from the Apollo 17 mission. This is sample 75055, which is not the catchiest of names. But this is a basalt that's really, really rare, because we think we actually know how it was oriented on the lunar surface when it first crystallized 3.7 billion years ago. And the reason that we think this now, whereas we didn't know before, is because of the images taken by the Lunar Reconnaissance Orbiter camera. So we now have really beautiful high resolution images of the lunar surface that we can use to interpret the context in which the samples were collected. So this is work I've been doing in collaboration with Jack Schmidt, who was one of the Apollo 17 astronauts, and in fact the only geologist they ever sent to the moon. And he's been actively working on kind of understanding the geology of the landing site ever since he went there. So the Apollo 17 mission landed where this star is here. And you can see all these little impact craters within this valley where they landed. And the sample that I'm looking at came from the edge of Camelot crater, so site number 5 here. And when Jack was sampling the edge of this impact crater, in his mind, he was thinking that this looks like a fresh, young impact crater. And so he was essentially just picking up bits of impact ejecta that had been flung out of the crater, and so were in a completely different orientation to how they formed. It's very unclear where they originally came from. But actually, when we got these high resolution images, it turns out the Camelot crater has a very, very different morphology. It's much, much smoother, and it doesn't seem to have that kind of ejecta layer over the surface. And so this has now been interpreted as actually subsequent mass wasting. And so the kind of interior of the impact crater has been kind of exposed over time. And so now, rather than sampling the upper impact ejecta, it actually looks like the subsurface bedding has been revealed within this impact crater. And that's really significant, because it actually means that these blocks that he was sampling, like this one here, are pretty much in situ. This isn't something that's been flung a long way by the impact. It's something that's actually been exposed as mass wasting has revealed what is beneath the impact site. And so these planar features that we see on these blocks on the lunar surface are now interpreted as actually good paleo-horizontal indicators. So this is telling us basically what the horizontal was when these samples formed, because these are essentially runny basaltic flows. So we know from evidence on Earth, so if you look at places like Hawaii or Iceland, where we have big basaltic flows, that they form horizontal planar features. So it's reasonable to assume that these would have originally been flat when the sample formed. And so the sample that they hammered off this block and brought back to Earth came from this box here, and I'll show you kind of how you can compare what we see if we zoom in on the photographs the astronauts took versus the photos that we have in the lab. So this is from JSC, so the Johnson Space Center in the US. They've documented every single Apollo sample to completely match the lunar lighting conditions in which it was collected. So this piece of tin foil here looks a bit scruffy, but actually that's to get the reflections and the shadows exactly right. So every shadow and every kind of feature that's picked out on this photograph from Earth, we can also pick out on the lunar photograph. So just to help you get your eye in, I can highlight some of the features between the two, and you can start to see how we can match up exactly the orientation of the sample in the lab versus the orientation on the lunar surface. So we've done quite a lot of photogrammetry to reconstruct the two. So once we know the orientation of the sample, we can then measure the paleomagnetic field, and we can then get an ancient field direction relative to the lunar surface. And so to do that, I was given a very, very small piece of sample 75055, so they're not especially generous with the material because they don't have an awful lot of it. So I got this chunk here, and just for scale, this cube is just 1 centimetre across, so quite a small piece, which I then further subsampled so I could measure lots of small pieces and ensure that I got the same consistent paleomagnetic measurements for all of them. So we want to see a consistent direction defined by all the samples, so we know that we're really measuring the true field. And so the dots here represent each of those subsamples that I measured on a stereographic projection. And you can see that they all point roughly northwest, and they're kind of horizontal. And so this is on the lunar surface in their present day orientation before we've tipped back to paleo horizontal. So that's what if we measured it on the lunar surface when they'd sampled it, this is the direction that we would have got. So very consistent, it's nice, they all point exactly the same way. And then we can tilt them to paleo horizontal and recover the steepness of the ancient magnetic field at the landing site. And so at the Apollo 17 landing site, the magnetic field had a dip or an inclination of about 35 degrees. And so we can use this to predict what it means for the different hypotheses of what generated the lunar magnetic field. So we can predict for a given latitude on the lunar surface what the steepness of the magnetic field should be. So if it looks like Earth's field, then this is the relationship between inclination and latitude. If it's more complicated because the moon is tidally locked, so it's not rotating very fast, then you would expect to get a much more complex variation in steepness of the magnetic field with latitude. And I plotted this up for absolutely every scenario that's ever been proposed for the lunar magnetic field. So there are some really weird and wacky ideas of you can have an impact on one side, which generates this plasma sheet that wraps all the way around the moon and magnetizes the opposite side. Comets have been proposed to do the same thing. You can even get little lava pools that generate their own little magnetic field. So I predicted what the steepness would be for all of these cases. And then we can plot them all on one graph of inclination versus latitude and see where our results sit. And so for the latitude of the Apollo 17 landing site, which is at about 20 degrees north, the mean of our data sits at this star here, and this is all the individual data points. And so this is consistent with this lunar-centric, so that basically just means moon-centric axial dipole. And so this implies that the lunar magnetic field is dipolar, very much like Earth's, and it's aligned along its spin axis. And that on its own is actually quite a surprising result, because the moon is rotating so slowly, you would actually expect, and this is, I'm not going to go into the details, but these are just some dynamo parameters that you can use to predict the magnetic field behavior. Because it rotates very slowly, it should actually have a very complicated field morphology. It shouldn't look like a simple bar magnet. So it should sit over here, but in fact, what we're seeing is something dipolar. So it should sit in this white region based on our observation. And so that might indicate something about the internal structure. It might actually be being filtered around this partial melt region that's been detected using seismology at the top of the lunar core. And that actually might be getting rid of some of those higher order signals. So we're seeing kind of a simplified version of the true lunar magnetic field morphology. And actually, that's a similar thing to what's been observed for Mercury. Mercury has a very, very large core and a thin mantle, and it's also predicted to be multipolar, but it has an almost perfectly dipolar field. And that's been attributed to kind of this filtering effect through the base of the mantle. So that's kind of all I think I've got time to go into today. So some kind of interesting, tantalizing results. We've certainly not solved it, but it certainly looks consistent with a dynamo. And it might be that we need to kind of think about the deep structure of the moon or gravitational forcing, so some sort of stirring by being coupled to Earth. But if you want to read about this in more detail, then we published this last year. So we kind of go into all the possible scenarios that could explain our observations if you want to know more. So I will finish there. I just want to thank all my collaborators on the project, and I'm happy to take any questions if I've got time.